Just trying to make this super hard.
Really? Whoa, it's like off the graph. That is not fun. Okay.
All right, Rolles Theorem. Here we go. Rolles Theorem should be pretty simple, I hope. Maybe. Rolles Theorem says this. If I've got some fancy graph floating around there, it's basically guaranteeing us some kind of maximum or some kind of minimum. It's guaranteeing one spot on that graph that has a slope of 0. So that's going to tell us a maximum minimum. So the stipulation for that is if I pick a value like right here, maybe call this A, and I pick this point right here. Okay, that right there would be f of A. Oops, f of A. It's amazing when you say something and your brain writes something. And then I'm going to pick this point right here, and we're going to call this B, and I've got f of B. Now what Rolles Theorem says is this. If I've got f of A and f of B, and these are the exact same, so these are at the same level, same height. If the graph is continuous and is differentiable all the way across that entire interval, which is from A to B, right? That's where our interval is going to be, so ignore the rest of the graph. That's going to guarantee me at least one spot on that graph where the slope is going to equal 0. At least one spot.
Only if they're the same.
If these values are the same height, it's going to guarantee me that I have somewhere on this little interval right here, forget about the rest of the graph, somewhere on this little interval right here, I have guaranteed a spot where I have the slope is going to equal 0. So there's going to be some value C right here, some value C, guaranteed that the derivative at some value C is going to equal 0. Okay? Now the stipulations on that are this. One, that your interval endpoints have to be the same height. Okay? Because if they're not at the same height, then there are really no guarantees. Okay? If I've got a graph of interval point A and then point B right here and here, I'm not really guaranteed a slope of actually equaling 0 right there. Okay? For example, if I pick my A right here and I pick my A or B right here, I wouldn't be guaranteed a spot between those intervals. Okay? But if I pick A and B right here, such that they're the exact same height, I'm guaranteed somehow, somewhere on that graph, I'm going to have the slope of some value C equaling 0. Okay? Stipulations are this. First off, f of A has to equal f of B. Okay? And that has to be on the interval, closed interval, A to B. If it's open interval, then you can't really have that point, so it kind of negates what we're talking about here. You can't have the endpoints be the same. And the other two things, it has to be continuous, and it has to be differentiable. Okay, so two key things that it has to be. If the endpoints are the same height, basically, it means I can take the derivative anywhere on that graph. Yep, differentiable, just take the derivative. Okay. There's some that I can't take the derivative on, but across this entire graph I should be able to. Okay. To tell it it's differentiable, it has to be a smooth curve all the way through. It can't have any sharp turns. Okay. If it has a sharp turn, we can't differentiate it yet. Okay. So I can pick a bunch of different values. Let's say that my f of A is like right here, and then my f of B is right here. I'm guaranteed one value right there, such that I have a slope that's going to equal 0. Okay. So my slope will equal 0. Okay. That seems pretty straightforward. I hope maybe at least the general concept. A couple things that can get taken off there. All right, let's do one problem, and then I'll show you maybe a couple exceptions to this Rolles theorem. Okay? Let's say I've got a function f of x equals, let's go x squared minus 3x plus 2. And I want to find f prime of c equaling 0. I want to find the c value. Actually, can I change that? Find c such that. I love the such that. It's one of my favorites. Such that. So find c such that the derivative at that point c equals 0, and we're going to say between the x-intercepts. Okay, now if I'm going between two x-intercepts, I'm hopefully assuming that my endpoints that I'm talking about, the x-intercepts, have the same height, right? They're both on the axis, right? So they're going to have the same height. So I got to find hopefully those 2 points, find out where my interval is going to be, and then I want to find some c value somewhere in there that's going to give me a slope of 0. Okay, so that's what I'm searching for. Okay, so let's first find my x-intercepts. So how do you find x-intercepts of a graph? Where it crosses the x-axis. Make it equal to 0. It said y equal to 0. Okay, if I were to have a graph like this and it has a point here and a point here or so, the y value on both those points is 0. So I'm just going to set this function right here equal to 0. x squared minus 3x plus 2 equals 0. And we'll solve for our x-intercepts on this one. So we'll just do a quick little factoring here. So we got x minus 2 and then x minus 1. And so that means 2 and 1 are my x-intercepts. Okay, so I've got some graph that I know right now. I know right now that I've got a point at 1 and I've got a point at 2. Some graph is either coming down like this or coming up like this. I'm going to have either a maximum or a minimum, guaranteed, no matter what, guaranteed. This is a continuous function, right? I can differentiate that pretty easily, right? So it's differentiable and continuous, and so that means I'm guaranteed a maximum and minimum between those intercepts for this graph. Okay, so let's go ahead and see if I can't find them. Okay, so to find the maximum or minimum, relative max, relative min, I need to find out where the derivative equals 0. So I just take the derivative of this guy. So I'm going to go f prime of x, and that'll give me a 2x minus 3. And I want to find my critical numbers. Okay, critical numbers is what we've been finding at least this weekend. And the critical numbers are where the function equals 0 or where it's undefined. So I'm going to set this guy equal to 0. No place where this is undefined, right? It's differentiable across the entire graph for this guy. And so I would solve this guy by adding 3 and then divide by 2, so the next would equal, looks like a 3/2. Okay, so I'm guaranteed a maximum or a minimum at 3/2. Okay, so now I just want to find which one it is. Is it a relative max thing? Relative maximum or relative minimum, one of those two. Okay, so I'm just going to go ahead and plug in positive 3/2 into my function and then see what you get. Right? So what do you get if you plug in 3/2? Did they do that yet?
Negative 1/4.
Negative 1/4. Okay, so my point is 3/2 and then negative 1/4. Okay, so I get negative 1/4. That's my point. So if I go to 3/2, I'm down a fourth. Looks like that point's going to be a minimum point. Okay. And this one is a parabola, right? So we have a parabola looks something like that. Pretend it went through that point. This one would be a relative minimum, right? Because it's relative to what we were doing. It's guaranteed to have a slope of 0. It's also on this one going to be an absolute minimum as well. Okay, no other points on this parabola are ever going to go below. Okay? So that's applying Rolles Theorem. That's finding two values that are the same height, and I'm guaranteeing a maximum in between that little zone right there. Okay? Does that make sense? Not too bad, I hope?
So is that C?
So my C value here, my C value is 3/2. So when it says find the value of C, C equals 3/2 is the value I'm looking for. If I plug in a 3/2 into here, right, that gives me 0. And that was what I was looking for. I was looking for a C value such that the f of whatever my value is 0. The derivative of f at whatever my value is 0. Okay? So I found the C values that work. I'm a happy camper. Okay? All right. Feeling semi-okay about this? Not too bad? I hope. Yeah.
Why did you need to find the negative 1/4?
Oh, just to see if it was above the line or below the line. If it was above the line, then it would have been a maximum. If it was below, I knew it was a minimum. Because if I have my two endpoints, if it's above the endpoint, it's a max. If it's below, it's a minimum. So I could have just graphed it, and then been done with it. But just for my own curiosity, I was just trying it out.
All right. Okay.
Cool. All right, let's do one more Rolles theorem real quick here, and then show you kind of the things to watch out for with Rolles, and then we should be good, hopefully. Okay. So let's say I've got a function f of x, and we're going to go x to the 4th minus 2x squared. And then I'm going to give you an interval on this one. Interval is going to go from -2 to 2.
So that's our 2 points that are between?
Correct. You can make them a closed interval on this one if you really want to, but it's kind of up to you on that one. For now, it's up to you. Later it will matter. Okay, so we're going to find all C. C's such that the derivative at some point of C equals 0. Now, it doesn't hurt to graph these. A lot of these, you want to try to do some of this stuff without a calculator, because when you guys get to the AP test, eventually there'll be a non-calculator section and then there'll be a calculator section. So if you just totally rely on your calculator, then half the test will be rough for you because it's a lot of no calculator stuff. Yeah.
So is -2, 2, is that a point or an interval?
Nope, that's an interval.
Oh.
And it's kind of tough to tell between a point and an interval. So sometimes that's why they kind of like to use the closed interval brackets, just because. But Yes, that's an interval. Okay, so the first thing you want to do is you want to check to see if this can even, if Rolles Theorem can even apply. Well, first off, if Rolles Theorem can apply, there's stipulations on it, right? First one is you have to make sure that f of a equals f of b. Okay, that's the first thing that you want to check. If you don't have those, if those two aren't equal, then you can't even use Rolles Theorem. It's out the window, right? If you have 2 points that aren't level, you're not guaranteed anything. Okay, you could still have something, but you're not guaranteed anything. I could have a point here, a point here. It could still have a point like that. It could still have a minimum point, but it doesn't have to. Okay. So first you want to check to make sure that my endpoints are actually going to be the same height or equivalent. Okay, so check the endpoints. So I want to do f of -2 and make sure that equals f of 2. Okay, which I think it does. Yeah, because odd or even, you know, this is an even function. It's going to keep it happy. So what do we get here? -2, so 16 minus 8 is 8. 8 equals 8. Is that right? I hope. Maybe. Okay, so we got 8 equals 8. Now that's going to be, that just tells me that they're at the same height. Okay, and the height of them are 8. At 2 and at -2, the height is going to be 8. Okay. Now I want to find all the points, all the c points, such that in between there, I'm going to have the derivative is going to equal 0. So let's go ahead and find the derivative of this guy. So I'm going to go the derivative of my x, or of my f of x, is going to be 4x to the third minus 4x. Okay, so I got 4x to the third minus 4x, so I want to set that equal to 0. The one thing to note here is that I took the derivative. The derivative, there's nowhere where this is undefined, where the derivative is undefined. That means that I'm differentiable across the entire graph. Okay, so that's one of the stipulations for Rolles Theorem, right? There was pretty much 3 of them. First one, the points have to be equal. Second one has to be continuous. All polynomials are continuous, though. And then the third one is it has to be differentiable across the entire thing. So if you find the derivative, if that doesn't have anywhere where it's undefined, then it's differentiable across the whole graph. So anyways, all right, so let's go ahead and set that equals 0. We would factor, take out a 4x, you're left with x squared minus 1 equals 0. And so then my 0 points here would be 0, and then plus or minus 1 looks like. So 1 and -1. Okay, so these are my critical values. These are my c values such that the slope equals 0. Okay, so I've found all the c values. All of these c values right here have a slope that equals 0, which is pretty good. Now I want to check, just to check to see what kind of points these might actually be, just ballparking it. If I were to plug in these values real quick here, let's just see what I would get. So I get f of 0. If I plug in a 0, I get 0. Right? If I do f of 1, if I plug in a 1, I get -1, I believe. And then the last one, if I plug in the f of -1, I get -1 again. Cool. Okay, so just by looking at what I have here, my height here was 8 and 8 for my point, right? So as far as my graph goes, I know I've got a graph that's going to be at -2 right here. I'm going to be up at 8, and then +2 up here at 8. And then I know at the point 0, I'm sorry, at the point x is 0, and x is 0, then y is 0. That's a point right there. F is 1, y is -1. That's right here. And then f of -1 is at 1 right here. And I know at each of these points right here, these are going to be 0. Okay, so I know I'm going to have a graph something like that. That point's going to have to be a minimum for it to be a slope of 0, right? I have a slope of 0 right here. This is going to have to be a maximum, and so my graph should look something like that. I've got a slope here, I've got a slope here. All those slopes are going to be 0. Okay? So a little rough sketch just based on a little bit of Rolles Theorem, and life is good. Yeah, what's up?
Where did you plug the x into again?
Into my original function. I just did f of 0, so I plugged in my critical values just to see what the y value was. Okay?
I thought that would make it equal 0.
No, if I plugged it in here, it would make it equal 0 for the slope.
Oh, so when you plug into the prime, it's equal 0. Plug into the original.
Give me some value.
It's gonna give
Right.
you a y.
It's going to give me an xy point. Exactly. Remember, this original graph right here, if I plug stuff into that, I'm basically just plotting points. That's all I'm doing with this graph right here. If I go to this graph, I'm finding out where the slope is 0. I'm looking for value, hills or valleys, basically. So,
I'm sure you probably already said this, but
Maybe.
those are relative minimums then, or point to the same?
These are actually, they're at the same height, so you could probably get away with calling them absolute minimums. They're not going to go any lower than this. However, you have to be a little careful first off. If they close out the interval, then yeah, you can say that they're absolute minimums. I'd probably just call them relative minimums because there's 2 that are at the same height, right?
Okay.
This right here would be a relative maximum, not an absolute, right? And then these 2 right here actually depends if it was an open interval or a closed interval. At the beginning, I think I gave an open interval,
Yeah.
right? So it wouldn't have an absolute maximum.
Okay.
Okay, if it were an open interval. Cool. All right, we feeling semi-okay about that? Rolles Theorem, not too bad.
So wait, what was the C?
C values were these guys right here.
Oh.
0, 1, and -1. Those were all my C values. Okay. Basically, my critical numbers, assuming that it was that my heights were the same. Okay. All right. Now, the one little catch here is if it's not continuous, then we're not really sure, right? So as far as Rolles Theorem goes, if I've got my A here and then I go over something like this and there's my B, I've got this some C value here that's going to be a maximum, right? I'm guaranteed right here that my derivative of derivative of C is going to equal 0. I'm guaranteed that, okay? Now, if it's not continuous, then we're not really sure, right? Because let's say I have a graph like here and an open circle and like here, right? I'm not guaranteed that I have a slope of 0 anywhere on that graph, even though these might be at the same height, okay? So that's why it's got to be continuous. That's why I can't have any holes or gaps for Rolles Theorem to work. And the other one is if it's differentiable across the entire graph. So let's say I had some graph like a point here and a point here, and then my graph does this. Okay, now this right here, is this still a maximum point? Yeah, it's still an absolute maximum. Now, is the slope of that 0? No, it's a sharp turn, and it's not differentiable, right? The function for this one would be something like some kind of absolute value function, right? Anybody know how to take the derivative of that? You can't, right? What you'd have to do is take the derivative on this half and that half and do like left and right limits and pluses and minuses. You know what I mean? That's not differentiable, okay? If we've got a sharp corner, I can still have a maximum or minimum, but I just might not have a value such that the slope equals 0, such that f prime of C equals 0, okay? So if it's a sharp turn, no C values that'll work there.
How can we tell if there's a hole from the equation?
Good question. There's two ways to check. One, you throw it on the graph, and you're still not going to be able to see it, though, because it's going to run right through it, right? The other is, usually you can tell if there's a hole, is if you're dividing by like x minus 3 or something like that, then sometimes there'll be a hole at 3. Okay, now when holes happen, usually holes happen on two different kinds of functions. One's a piecewise, and the other is if I have dividing by x minus 3, 3 would be an asymptote probably, right? But if I had some kind of x minus 3 on the top with some other stuff, blah, 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 right, and those cancel, that creates holes. And so usually I check to see if there's a denominator, and then that's where you might have a chance. So that's where I'd be worried about it. Okay? So, anyways, everybody okay with kind of the stipulations on rolls? It's not too bad. Got to be continuous, got to be differentiable for you to have a slope at 0. And we're happy. Okay? All right, cool. 176.